Good afternoon, everyone. Thank you for coming to the talk colloquium. I'm very happy to introduce Penny Haxell, who is a professor in our department and a longstanding expert in graph theory, and will tell us about graph theory today. Thank you.
Okay, thank you. So I'm going to talk about this rather vague-looking topic, graphs with high chromatic number. I'll be very much more specific about it in just a moment. This is really a talk about really basic graph theory questions. So you'll, especially if you've been in my 442, 642 class, which I'm happy to see that some of you have, you will see a lot of familiar looking things as we start out here. Okay, but just to set the stage and make sure everyone knows what we're talking about, I'm talking about coloring the vertices of a graph. So to say that a graph G is K colorable means that you can partition the vertex set into K so-called independent sets. So inside an independent set, you don't have any edge of the graph. That's what it means to say that G is K colorable. Whenever we teach coloring in graph theory, the first thing we do is we give this definition. And the next thing we do is we point out that there's a simple greedy algorithm that will color a graph with its maximum degree plus 1 colors. Right? So if every vertex has degree at most delta, this is what the notation I use for the maximum degree, then you can just color the vertices one by one with the lowest color out of 1 up to delta plus 1 that you can give it, so that it has not got any of its neighbors previously colored that color, and you never have to use any more than delta plus 1 colors because nobody has degree more than delta. Okay, very easy. So that's a natural upper bound on the chromatic number of any graph is delta plus 1, where delta is the maximum degree. And then you ask, well, are there graphs that actually need a delta plus 1? And sure, you can think of some. The obvious, most obvious example for every delta is the complete graph with delta plus 1 vertices. You need a different vertex, a different color for each vertex, and the maximum degree is delta, so definitely you can't do any better for that one. And also, when delta is 2, in a very special case delta is 2, you also have every odd cycle. Is an example. Okay, so that's the first thing we learn in the first 10 minutes of the class on coloring graphs. And then we ask the question, when does it happen that you can't actually do it with delta? When do you really need delta plus 1 colors? And then the next thing we do is we learn Brooks' theorem, which tells us that basically those two examples we saw on the previous slide are the only examples where you actually need delta plus 1 colors, if you're talking about a connected graph. So let me say it this way, because I want to specifically compare this to another statement later. So as long as we're out of the case delta equals 2, so that's the kind of a special one, if a graph with maximum degree delta is not delta colorable, then it contains a complete graph of with k plus 1 vertices. That's I call this a clique, k delta plus 1. And if it's a connected graph, then it is the clique. There are no other vertices possible. Okay, so that's Brooks' theorem, and has a very nice proof, actually many nice proofs. Nice proof that basically uses a modification of the greedy algorithm. That's what we learn in our class. Okay, so to just say it another way, if delta is big enough, where big enough means at least 3, then the clique with delta plus 1 vertices is the only obstruction to coloring with delta colors. Great. Okay, so we learned that, all very nice material. And then what we do in the class is we move on to something else, right? But then maybe there's that student in the math class who has, wait, what if delta minus 1 colors are not enough? Natural question. So we think, well, obviously, again, if G contains a K delta, then it's not a delta minus 1 colorable. That's obvious. So could it be also the case that this is the only obstruction? And, well, you think about that for a moment, and of course, whenever you have a question like that, you always reach for the Peterson graph to see if that's a counterexample, and indeed it is, right? A counterexample. Easy to notice that the Peterson graph is 3 regular. It does not contain any K3, doesn't have any triangles, but you can't color it with 2 colors. It's not bipartite. And there are actually zillions of graphs of maximum degree 3 that are triangle-free and not bipartite. So yeah, no, lots of examples. Definitely not true. Here's another example with a higher delta. This one has degree, it's actually 6 regular. You get this is the so-called cube of the 11 cycle. So you take the 11 cycle, and then you and they give Ricardo a call, and he tells you that you should join every pair of vertices at distance 2 and distance 3, so that's the cube of the 11 cycle. And right, so delta is 6. It does not contain a K6, actually doesn't even contain a K5. You can see that the biggest complete subgraph here has size 4. But I claim you cannot color this with 5 colors, sorry. So you really need 6 colors to color it. Why? Well, there are 11 vertices, and look at any vertex. What are the vertices that are forming an independent set with this vertex? Only these ones on the other side of the graph that are forming a clique. So the independence number is 2. So every color class has size at most 2, and so definitely you cannot color this with 5 colors because you've got 11 vertices. Okay, so here's another example, and you can go on and think about many other examples up to delta equals 7. Here's one with delta equals 8. Here I've got 5 triangles which I put around in a cycle and then join all of these across in complete bipartite graphs. And so this is 8 regular. Every vertex has 3 neighbors there and 3 neighbors there and 2 neighbors in its own triangle. So it's 8. So delta is 8. Again, there's no K8. There's not even a K7. The biggest clique you see is here, size 6. And you can't color with 7 colors, actually for the same reason as we saw in the previous example. The independence number is 2. The non-neighbors of this vertex is simply this clique. So the independence number is 2, but the number of vertices is 15. So you can't color with 7 colors. Okay. Okay, so there's another example. You say, okay, well, yeah, no, this thing is definitely not true. But then you start to think, can I think of any other examples where delta is bigger than 8? Well, then you probably will get stuck. And you will then maybe look things up and discover that there's a famous conjecture due to Borden and Kostochka from 1977, which basically says that if delta is big enough, and now big enough means 9, then if G is not delta minus 1 colorable, then it should contain a K delta. Okay. So a very natural question. Let me give you a brief and simple argument that tells you that if G is not delta minus 1 colorable, it should at least contain some biggish clique, at least something of a size that depends on delta. Okay, so let's see an argument for that. And again, if you've been in my class, you might recognize some ideas here. Let's take G, and let's take a max cut in G. So we partition it into 2 pieces, and you want to maximize the number of edges crossing over. Okay, well, it's easy to see that if you do that, and if you look at any vertex, then its degree on its own side is less than or equal to its degree on the other side. Because if not, then you just put it on the other side and increase the size of the cut. Okay? Okay, so every vertex here, its degree you can think is being cut in half at least when you do this partition. Okay, so let's think just for a moment about odd delta. And then what that says in particular is that if I look at the maximum degree of just what the graph that I see on this side, its maximum degree, let's call it delta prime, is at most delta minus 1 over 2, because this number has to be at less than or equal to the number going across, and it was odd. Okay? Okay, so basically the maximum degree gets cut in approximately 1/2. Well, okay, now let's look at this subgraph that we see on this side. And let's ask, suppose that it does not have a clique of size delta prime plus 1. Delta prime is the maximum degree on this side. If it doesn't, and as long as this number is at least, delta prime is at least 3, well then Brooks' theorem says that you could color with, you don't need delta prime plus 1 colors, you could color with delta prime colors, which remember was at most this number. Okay, so if I don't have a clique like this on this side, I can color with this many colors. And if I didn't have a clique like this on this side, I could color that many colors, and then I would be finished with 2 completely different color sets coloring this graph with delta minus 1 colors altogether. Okay, so that tells us that at least we can depend on there being, in a graph whose chromatic number is really delta, we can depend on there being a clique of size about half delta, just by this simple argument. Okay, so that simple argument was observed already by Borden and Kostochka when they introduced this conjecture. And since then, there have been many, many papers on this question, a very important and kind of influential question. And I list some of them here, improving from about a half delta to 2/3 delta, Emotion in early 80s. Delta minus a constant, a very important step later on, and then improving these things and so on in various other steps. And I'll stop here at the bottom, a second from the bottom. This is now the record in terms of results of this type. Cranston and Rayburn proved that there is a delta minus 3 clique whenever delta is large enough, and large enough means 13. Okay, so that's the kind of state of the art looking at the question from this point of view. If you are prepared to go with a very large delta, then Reed showed it's actually the full conjecture is true. But so this is a probabilistic argument, and very large means very large, like 10 to the 14, probably could be reduced somewhat, but anyway, that's really kind of very far from the realm of delta equals 9. But still, very important to know that it is solved as long as delta is big enough. Okay, so that's what's known for the general question, and then, as you can probably imagine, there are many, many special classes of graphs for which this has been studied and proved, and I'm not going to tell you anything about the details of those. By the way, I write things in green if I don't really want you to be able to see them. So don't stress out if you can't see them. You're actually not supposed to. But this is right. This is a long list of names that I'm not going to tell you and the results that they did. Okay. Anyway, message is graphs with high chromatic number, high in terms of delta, should contain large cliques, and the whole question is about what does high mean, what does large mean. Okay. So I'm going to try to give you a picture later on about the main idea that is behind all of those results except for the Reed result, which has a different approach. That's a probabilistic approach. And it goes kind of like this, and the ideas you'll see here, we saw them already in our very simple proof with the max cut. The general ideas. So the ideas go like this. You first color as much of the graph as possible using delta minus 1 colors. Maybe you assume the whole graph is critical, or maybe you just have a critical vertex. Doesn't matter. Anyway, you have some uncolored vertex. And then you partition the graph somehow into parts, like we did with the 2 parts, but this turns out to be more parts. And we understand somehow the chromatic numbers of the parts well. And we'll see a bit more what that means specifically. And then we have our great tool, which is Brooks' theorem. So we apply Brooks' theorem in these parts. It's actually almost every part, to conclude that, well, almost every part contains a clique component. And at the end, which is the hardest part, so this thing is not working, is to kind of show that lots of those clique components actually have to kind of bundle together into a kind of big snowball and be a big clique in the whole graph. So that's a kind of bird's eye view of the approach which is taken in most of those theorems I showed you. However, let me just say a little bit about where can you go further. Well, of course, we asked the question about delta minus 1. Delta minus 1 colors are not enough. How about delta minus t for a larger t? And sure enough, it is possible to extend these techniques and ideas to prove a more general theorem. And so this is something one can do. So for chromatic number delta minus t, how do the numbers go? If delta is big enough in terms of t, and it happens to be some quadratic function in t, then the clique number, so the maximum size of a clique in your graph, will be delta minus, again, some function of t. Right, so the Cranston and Rayburn result is this when t is 0. So it says a delta minus 3 is the clique size when you have a chromatic number which is really delta. Okay, right, so that's an extension. Now you might wonder, is there a conjecture about such extensions? Because it was a natural question, and Borden-Kosachka was really conjecture in that case, and there is. This is a general conjecture due to Reed, not specifically aimed at graphs with very high chromatic number close to delta, but in general tries to capture the chromatic number in terms of the maximum degree and the clique number. And the conjecture is that basically the chromatic number should be bounded by a kind of average of those two things. Again, our picture for delta equals 8 is it shows that this is best possible, and many other things also show it's best possible. This other graph I showed you is also tight for Reed's conjecture, and there are many others as well. Okay, so if we look at Reed's conjecture and ask what does it say specifically for a chromatic number being delta minus t, where you're thinking about t as being some small constant, if you reinterpret this, it says that there should be a clique of size like this, delta minus, well, a linear function in t. And so the theorem I showed you gave a quadratic function there of t, and this is conjectured to be a linear function. So here is already a kind of intermediate, hopefully not as hard as Borden-Kosachka conjecture question. Can you improve these things so to get a delta minus some linear function of t, not necessarily this? Don't know. Okay. Anyway, so I'm just going to mention one more thing before I start to talk about those proof ideas. And for this, it's actually more convenient to speak in terms of critical graphs. So what do I mean by a critical graph? A k-critical graph is a graph G whose chromatic number is k, but if you remove anything, then its chromatic number goes to k minus 1, or lower. Yeah? So if you remove a vertex or an edge, then it becomes k minus 1. Actually, I'm only going to talk about vertices here, but we can have this as a definition. So with this definition, one can restate the Borden-Kosachka conjecture in terms of critical graphs by this. For every k, at least 9, the only k-critical graph whose maximum degree is less than or equal to k is kk. That's what it says. And note, interestingly, kk doesn't even have delta g equal to k. It's actually k minus 1. So it's kind of maybe a bit surprising. But that's the restatement of the conjecture. And I'd like to mention that, as shown very early already by Kosachka, and also Kathleen had similar ideas, you can actually reduce this whole conjecture to asking about the case exactly 9. Because if it's true for 9, then in fact the whole conjecture is true. So you can reduce the whole question to the case delta equals 9, which seems kind of manageable, right? Graphs of maximum degree 9, how difficult can they be? Okay, well, they can be difficult, as it turns out. So in this vein, I wanted to mention one more thing. Now, here is a definition which I think I won't bother going through because I don't think this is a really kind of very kind of significant definition. And anyway, it leads to a theorem which says something about this definition. But let me just jump to the corollary of this theorem. And this comes with a kind of general confession about this whole topic of the Bordin-Kosatka conjecture. We all saw that this graph, we call this C5K3, it's a product of the cycle of length 5 with the triangle. We saw that this was an example showing that Bordin-Kosatka conjecture, you had to start at least 9. As a matter of fact, so because this is actually an 8 critical graph with delta equals 8, which does not satisfy the condition. But the truth is, this is the only one we know about. We don't know any other 8 critical graph with maximum degree 8. This is the only one we know. And so, a corollary of that theorem that I didn't tell you is that if it's true that this is the only one, then again, the Bordin-Kosatka conjecture is true. So in other words, if you want to prove something about graphs with maximum degree 8, that's this. That will already take care of the conjecture. So that's a reduction that can be done. So especially if you're kind of, I don't know, computationally minded, I have no idea how you would look for other 8 critical graphs with delta at most 8, but if you had a good way of doing that, and if you found one that was different from this, then that would at least really change the picture, add a lot to the picture that we have right now. Okay, so that was a little bit of an aside, but I might get back to one thing about that later at the very end. But anyway, let's go back to these to the extensions. Actually, again, I'm not really going to say anything different about this theorem than the Cranston-Rayburn and other results, but I'm just stating it here again. But just to say that I'm now going to tell you something about the main technique that all of these results, including this theorem, use. And it's a really very nice technique which was developed by Mojan, one of the early people to study this conjecture. And it's based on these special partitions, which I'm now going to tell you about. Okay, so because they were due to Mojan, I'm going to call this Mojan partition. And what is a Mojan partition? Now, let's just make sure we establish the setting here. I'm going to have a graph G that cannot be colored with delta minus 1 colors. And its delta is congruent to 1 mod 3. And from now on, just think about this being the number 10. So on my slides, it's going to be the number 10. That's because I couldn't really fit anything much bigger on the slides without struggling. So I have a graph. Its maximum degree is 10. You cannot color it with 9 colors. And we are going to learn that it has a large clique in it. That's how it's going to go. But this is the same argument for everything 13 above and everything else. Okay. So, right, what is a special Mojan partition? So there's some complicated looking things here. I will try to elucidate these things. So first of all, it's a partition of the vertex set. Instead of into 2 parts, now I'm going to have Q parts where delta is 3Q plus 1. So in my pictures, it's going to be 3 parts. But think of it as being more parts if you want. Okay, partition into that many parts. There's also going to be one special part, which is denoted S for special, and one special vertex, which is going to be in the special part. That's all. All of the parts are going to be 3 chromatic. Their chromatic numbers will be 3, each one, except for the special part, which will have chromatic number 4. And the whole chromatic number of the whole graph is going to be 3Q plus 1, so that's going to be, in our case, 10. So that's a Mojan partition. Now, how do I get one of these? It's easy to get one of these from our graph, which is not colorable by delta colors, but let's say it has a critical vertex, that I can remove a vertex and its chromatic number goes down. So we started with 10, I remove a vertex and it goes down to 9. Okay, so how can we find such a partition? Well, we take a vertex, remove it, its chromatic number goes down to 9. So we have 9 colors, and just take those 9 colors, partition them completely arbitrarily into 3 groups of 3 colors each, and take the vertex classes of those colors, and that gives you the partition. That's the partition. Now, what about the vertex I removed? Well, now just stick it back into an arbitrary part, call that the special part. The chromatic number of that one goes up to 4, and that's it. And that's a partition, that's a Mojan partition according to these definitions. So it's easy to get such a partition. Okay, and so when we do that, just one little piece of terminology or notation, the component of the special part containing the special vertex we call act M. That's called the active component of the partition. Okay, picture time. So here we go. So there's my V. I removed it, and then I colored the graph with 9 colors. So now I'm really talking about 10. I colored the graph with 9 colors. I partition the colors arbitrarily into these parts, and then to get the Mojan partition, I stick V back into one of the parts, and then its chromatic number goes up to 4, and that's it. So that's a Mojan partition. Okay. So what can we say about them? Lots of fun things. Each one is an easy thing, but they all add up to being something very nice. Okay, so let's start. My critical vertex V, I claim, has degree 3 into each part. Yeah? If V had a degree only, say, 2 into this part, well, this part, color it with 3 colors. The neighborhood of V inside this part only has size 2, so you could actually just stick it in there and color it also with 3 colors, and then you color the whole graph with 9 colors. Okay, fine. So every vertex, that V, the critical vertex, has degree 3 into each part. Right. Well, remember that its degree was 10 at most. So it has degree 3 here, 3 here, at least 3 here. So actually all the degrees are either 3 or 4, and only one of them can be 4. Okay, good. So that was easy. Now, next fact. Well, there's a component C in each part, so that V has degree at least 3 into the component. Well, for exactly the same reason. Now, I had that big blob now, but maybe I'll just partition these into their components, and V had better have a degree 3 into some same component here, otherwise we could do the same thing. It had a degree 2 here and 1 here, then change the names of the colors here and here so that you can color V as well. Okay, so fine. So in every part, V has got at least 3 neighbors into some component. Okay, right. Okay, now I'm going to look at the active component, and I'm going to look at vertex W in it, and suppose W is critical in there. So here's W, and it's critical in this component. Remember, that means that if you remove W from this whole part here, the chromatic number will go down to 3. Okay, so W is critical in its part, like that. Well, then if I remove it from the whole graph, then also the chromatic number goes down to 3, right? Because we had just 3 here, and it's done. Okay, so W, if W is critical in its part, then it's actually critical in the whole graph. Okay. Okay, so it's critical in the whole graph. Oh, well then now suddenly we have a picture looking like we did before when we got the first Mojan partition in the first place. Then now I could put W into any part, and it would have to be critical there too. Right? If I put it here and the chromatic number didn't go up to 4 here, well again I'm done coloring it with 9 colors. So if it's critical in its own part, then it's critical in every part. Okay, fine. It's critical in every part, so there it is. So it's starting to look a lot like V, in fact. Okay, so it's like that. What else? Well, if it's critical in its part, then moving it to any other part is another Mojan partition, because it looks just like we were with V. Move it to some other part, move it to a part like this one, that's another Mojan partition. Okay, so if we have a Mojan partition and we had a critical vertex, W started in the critical vertex, as a critical vertex in the active component of V there, then we could get another Mojan partition. So this suggests that there might be several Mojan partitions. Okay, there are. Now, let's take some special ones. Minimum Mojon partition. Again, here's an idea from the assignment 1 in CNO 442, 642, that let's choose a minimum Mojon partition that minimizes the number of edges inside the parts, first of all, and then after that minimizes the degree of the special vertex into its own part. Okay, so that's what minimum means. First of all, I minimize all the number of interior edges in all of these, just the sum of those, and then I minimize the degree of the special vertex in its own part. So it's a minimum Mojon partition. Okay, so far it's all looking a little bit boring, but okay, but let's go on with some facts. So W, critical in its part, moving it to any other part, that it has degree 3, gives another minimum Mojon partition. If I start with a minimum one and I move W to another part where it has degree 3, what happens? Well, its degree here is at least 3, because everyone has that property. And if I move it over here where it has degree 3, well, I lose at least 3 edges and I gain at most 3 edges. So it's going to be also minimum. If I put it there, that's another minimum Mojon partition. Oh, so what? So, okay. So that's another minimum partition. Now, there is something that says key fact. It says, in a minimum Mojon partition, M, the active component has a maximum degree 3. So let's go back. Here is here's a minimum Mojon partition. Here's the active component, contains the special vertex. That part has chromatic number 4. And it turns out that actually this has maximum degree 3, which is a little bit maybe unexpected. So it turns out that if we had a vertex of degree 4 in this active component, then there would be some vertex of degree 4 in this degree at least 4 in this component that's critical. Does it have a degree at least 4 in this part and is critical? If I move it to where it has degree 3, then I actually reduce the number of total number of interior edges, because I lose 4 here and I gain only 3 there. Okay, now, and I'm not telling you the proof of that, but it's an easy elementary proof, but just takes maybe 5 minutes, and I don't want to overload you. Yeah. It would ruin the kind of cartoon approach to my thing here. Okay. So it's a vertex degree 4, it would be critical. Okay, so this tells us that the active component here then has maximum degree 3. Right, yeah, that's a contradiction. Okay, this has maximum degree 3. Well, but wait, this component is the only component that has a chromatic number 4. Its maximum degree is 3. So, by Brooks' theorem, it's not an arbitrary, mysterious blob like that. It's a K4. So now we suddenly know what this component looks like. It's a K4. Okay. Well, it's a K4. Note then, every other vertex in this component is critical in its component. And remember, they can all move anywhere else. And whenever they do, right, that's what I just said. Whenever they do, here they are, the active component has all these other critical vertices. And whenever they move to another place, like this one, this vertex moves from here to somewhere where it has degree 3. And the moment it steps into that component, it finds out that that component is, where is it? Also a K4, for the same reason. Okay, and then so all these are critical. And now suddenly you have this way of moving vertices around in this partition, and every time somebody new steps into a new component, it's not this mysterious dark blob anymore. It turns out to be a K4 when you step in there. And so you can discover, one by one, all kinds of new components, and they're all going to be K4s when you step into them. And of course, when you leave them, they become triangles again. So after many moving around steps, like this, we discover that the whole picture is this nice, any place we actually visited in this moving around process, are all a bunch of triangles, and then wherever we stop right now, that's a K4. So all these kind of very basic properties of the Mojan partition nicely kind of end up giving us a very clear picture of at least part of the graph, the part that we can actually see when we make all these moves. Okay, so that's the picture there. All right. Now, any sequence of minimum Mojan partitions, we're always staying in this minimum case, that we get this way, so-called move sequence. And the whole game here is to choose some appropriate conditions for a move sequence that will lead to properties that you can use. So what we do in the proof is choose an appropriate type of move sequence. We call it a depth first move sequence that has the following property. If I define these things which I call houses, so what is a house? It's basically a component of one of these parts, and you just watch the component and what happens to it during the whole move sequence. And what happens? Well, at some point, the moment you discover, the moment someone steps in and switches a light on, discovers it's a K4. And then, of course, when someone leaves, it becomes a triangle, and then you sit there, and let's just look at this house, and then there's this move going around, all these moves, and then maybe someone comes back in, and then it becomes a K4 again, and someone leaves, and it's a triangle again. So always in this house, you see some occupants, and they're always either forming a K4 or a K3, all the time. Okay. With an appropriately chosen move sequence, so appropriate restrictions on this move sequence, we can guarantee various useful properties, and the main one that we use in the proof is we're able, just by a simple counting argument and an appropriate choice of move sequence, to find out that some house here gets at least 7 is delta minus 3, at least delta minus 3 visitors in all this special type of move sequence. And then it turns out that because of our definition of this move sequence, which I'm not able to tell you because it's a little too complicated, but let me just tell you that you can do it, you end up finding out that actually all these visitors who ever visit this house all stick together in a great big clique in the whole graph. And so you get a delta minus 3 clique, and it consists of a bunch of these small cliques in all of the other parts except for one. So that's why the delta minus 3. You can't do it for all of them, but you get all except one. So that's how the argument works. Okay, so that was a kind of then a little bit more in-depth overview of how the theorem that I told you specifically is proved, and also these ideas were used in many of the earlier results, and especially Mojan, who invented this scheme in the first place, which is a very beautiful idea. Okay, so you might think, as I told you that thing, if you were able to stay awake, that it looks somewhat algorithmic, and it is. So it really does give you a step-by-step way of either finding a delta minus 1 coloring of the whole graph or a delta minus 3 clique. And it's an efficient algorithm. Okay, good. So we're getting close to the end. You'll be glad to know. I'm just going to return now to the small deltas case, just for a few minutes, because I would like to leave you with some potentially more approachable open questions. Because Borden-Kosacha conjecture, that's hard, and I think other things to do in that sort of realm are hard, but this might lead to some somewhat easier questions. So remember I told you that if you can prove the Borden-Kosacha conjecture for delta equals 9, then you proved it for all. And if you could prove that C533 was the only one with delta equals 8, then it's still true. So there's maybe a possibility of stepping one step down further to graphs of degree at most 7. So to see this, or for me to explain that, I'm going to return to this case. So we're going to think now about k-critical graphs where k is at most 7. And I won't tell you why this statement is true here, but it's an easy thing to verify. You can verify it for yourself. So if you have a k-critical graph, where k is at most 7, and if you have a vertex of degree k minus 1 in it, that is possible. Vertices would have degree k minus 1 or k in such a graph. And if you take a vertex of k at degree k minus 1, and you split it into 3 vertices and share out the edges as evenly as possible, and then you attach this gadget, it's simply k minus 2 new vertices forming a clique, and just join them all to your three new vertices like this. This graph is also k-critical. It's an easy exercise to verify. Okay, so if we had a k-critical graph with k at most 7, we could get a bigger one by doing this, as long as we had a vertex of degree k minus 1. Now, if k is at most 6, then when you do this, you will get another vertex here of degree 5. So if I had a vertex of degree 5, I would get another vertex of degree 5 here. Okay, so then I could do it again with that vertex of degree 5, and again by that vertex. And you could do this infinitely, and you could create infinite family of k-critical graphs for k less than or equal to 7, for delta is k, at most k, you can create an infinite family, no problem. However, when k is 7, when you do this, you lose your vertex of degree 6, and you don't get any more back. So you can do this, say, starting with k7, that has 7 vertices of degree 6, but you can only do it 7 times, and then you will get stuck. You will not get any bigger. So that's a way of constructing, okay, this is what I just said for delta and most 6, and there are other constructions as well, right? But for the delta 7, if you start with a 7 critical graph, k7, you can only get up to 56 vertices, and then you don't get any more examples. There's another 7 critical graph, which is actually a subgraph of that C5K3 thing that I showed you, which is also 7 critical, and it has some vertices of degree 6, and you could do that, and you could get some more examples up to 34 vertices, but then you get stuck. And here again, then we don't actually know any other examples. So, to close, here are maybe some more manageable, approachable questions, and this is the one I was just talking about. Is there an infinite family of 7 critical graphs with, what do I have to do here to, well, hello. Well, oh, it came back bigger. I don't know why. Okay, well, sorry, I don't know what to do about that. Okay, oh, but they still fit. Okay, fine. No, don't go off. Hello, okay, yes, all right. Okay, it's telling me. I mean, I still have 5 minutes, but anyway, I am going to end. Right, very quickly. Is there an infinite family? Are there any more besides the ones I just told you about? I don't know. So this is an interesting question, I think. Any more of those? Well, there's a question I asked you before, I mentioned before. If there's any other 8 critical graph with delta equals 8, different from the one I showed you, that would be interesting. And then a question related to this, maybe, is there some further reduction? So as there was from 9 to 8, related to this question, is there a further reduction from 8 to 7? So can you reduce, so can you find a statement about 7 critical graphs with delta equals 7 that would imply the Borden-Kotochka conjecture, maybe related to the existence of these graphs here? I think another interesting open question. Okay, thanks for your attention. That's all I have to say.
Thank you. If there's any questions, please wait for the microphone for the recording.
Yeah, I didn't fully follow. I mean, like you didn't show the movements and so on. But I was wondering whether there are some cases for degree or no chromatic number that are for which it's easy to prove the Ritz conjecture because of some divisibility or remainder issues?
Yeah, so so in fact, well, with these arguments, definitely 1 mod 3 is the natural case to consider. Now, so why 3, right? So why didn't I partition those into things of chromatic number 4 instead? Or maybe some 3s and some 4s, or maybe a whole bunch of other things. You can. And all that does still work. But actually, if you do with 3, you get the best, you get the most precise results. So you might ask, so if you can prove it for a 1 mod 3, what about the next delta? Add 1 to that. And a very similar statement will be true, but there's a little bit of weakening going on up to sort of between, say, 10 and 13 or something like this. But actually, once delta gets big enough, then you can also just simply do this reduction, that if you can prove it for a certain delta 0, then it will automatically follow for larger deltas. Yeah. So there's a little bit of business about divisibility at the bottom of the range, but then after that, actually, you get everything. Yeah.
Thank you.
Yeah.
So I know you didn't want to get into the exact definition for the moving process, but could you maybe give a little bit of intuition on what types of ideas the algorithm wants to see to actually be analyzable?
Right, yeah. So the move sequence, so it's actually not so difficult to describe. It goes, so I think of the move sequence, by the way, as a kind of very a dynamic thing. You have all these houses that are there in the village in the dark, and someone steps into a house and switches on the light and discovers it's a K4. Great, and then one of those occupants gets on a bike. Maybe there's only one bike, and goes to another one and discovers wherever that person goes can go. They discover another one, and so on. So the depth first. Basically gives everyone an order in which they go, and it's a sort of depth first. So the first house is, the light is on, and now everyone, one person goes out, and then is going to do all the things that person can possibly do, and then come back. But as soon as he or she steps into the next house, then suddenly then that one stays there, and all the other ones get priority, and they go, right? So it's a depth first thing. And the thing that it ensures is basically allows you to keep track of the whole status of the system at every stage. And it's a little bit hard to explain why that is the case. But one of the properties of it is that if all these things happen, you can imagine this whole kind of process is running out like that, and then eventually comes back to, and when that person who left stepped back, then actually this status is exactly the same as the status as when that person stepped in. And that actually really helps the analysis a lot. Yeah. So controlling those move sequences is kind of the whole, the key to getting everything to work. Yeah, yeah.
Other questions? Let's thank Penny again.